Oh, yeah. Yeah, my nomenclature and stuff.
Uh-huh. What is this? I'll start you off kind of.
Yeah, I've been practicing.
We'll start you off basic. What is this one?
Sodium sulfate.
Good. So this is a metal or non-metal? Sodium is a metal or non-metal? It's a metal. This is a polyatomic anion, and its charge is -2. What kind of compound is this?
Ionic compound.
Ionic, good. All right. What would this be?
Lead chromate.
Okay. Let's see. Is lead one of the multivalents? Can lead have more than one charge?
Transition metal.
It's not a transition metal, but it's on that verge. It's all the transition, or some of the transition metals, and then these three guys right here. We got indium, tin, and lead can be multivalent. So the key is to know the charge of your polyatomic ion. Which anion is this?
Yeah, it's either +2 +4.
Yeah. So what is the chromate?
And it cancels out, so it has to be a +2. It's a -2.
Okay, so then this would be Pb +2. This would be CrO4 -2. So it would be lead 2, and then what's the last one? I want to know the Vesper. I want to know the electron pair geometry. This is just the general shape that it takes on. And then depending on the number of lone pairs, I can determine the molecular pair geometry. Okay. So what is the first step? Kind of put valence electrons. So let's look at what's going on. Sulfur's got how many?
That's good.
Sulfur has
6.
Very good. And then fluorine has how many?
35 in total.
35 in total because it's a halogen and there's 5 of them. Okay, so when we do 6 plus 35, okay, let's make this an ion. We'll put a minus sign here. Is everybody okay with that?
Can I go in there? I'll put it there. Yeah.
Okay, so what do I do with that extra electron? How does it affect my number of valence electrons?
You add 1 because of an ion.
Good. So this minus charge causes us to add 1 electron, and that's going to give me a total of 42. So now I have sulfur, and then typically how do we determine which is the central element in our Lewis structure? How do we determine that if it's not symmetry, like in this case?
It's usually the most electronegative.
It's actually the least electronegative.
Oh, yeah, the least electronegative.
It wants to be able to share its electrons as frequently as possible. Okay? So now in this case, we look at this and we say, all right, what do I add? I need to add my bonds. Okay, so let's put a single bond since they're halogens. They typically only form 1 bond here. And how many electrons do each of these lines represent?
2.
2, so that would be a total of 10 bonding electrons. So that leaves me a total of 32 lone pair electrons. Any questions so far? Should we review from the last exam? So now, where do the lone pair electrons go?
Around the outer atoms.
Okay, good. Let's put some on fluorine.
I don't understand that. 42 minus 10. 42 minus 10. So now 106 electrons divided by 3 to 1. 3.
These are the bonding electrons.
No, 1.
Shirley, to answer your question. So here we have 6 electrons, 5 fluorines. So that's a total of 30 lone pair electrons. So I got 2 more left.
Because sulfur is in the third period.
Very good.
So you can give it a low.
Yeah, so I've already violated sulfur's octet by giving 2, 4, 6, 8, and 2 more. And that's okay, because anything on this third period or below has access to this D block. So 10 more electrons can come in. Okay? So now, as a result, you should be able to give me everything I need to draw a 3-dimensional shape. Shirley, your microphone's a little too sensitive. I'm going to mute you unless you have a question, okay? Can you mute yourself?
Okay.
And then if you have a question, just raise your hand. Kevin, you can unraise your hand by clicking the hand again. That way I don't think you have a question.
Oh, okay.
No worries. All right, so then we have the 2 lone pair electrons. So the way you go about doing this is you say domains. How many domains do I have? Okay, the domains include the bonding domains or the lone pair and the lone pair electron domains. So how many domains do I have?
5 or 6. 6.
5 or 6? Which is it? 1, 2, 3, 4, 5, and then 6 domains. So right away, when you write down 6, you should be able to tell me the electron pair geometry. What is electron pair geometry for the shape?
Octahedral.
Very good. So we know it's octahedral because it has 6 domains. What if it was 5? What is it?
Trigonopyramidal.
Very good. If it's 4?
Tetrahedral.
Good. Somebody's going to do this tomorrow. And then 3?
Trigonoplanar.
Okay. All right, so then now how many of these domains were bonding domains?
5.
5, very good. And then 1 lone pair. So this is what tells you what your MPG is, okay? So the fact that we have 5 bonding and 1 lone pair domain tells us that our MPG is what?
6. Wait. Octahedral? Octahedral. Seesaw.
Square.
Or square.
One of the square.
Planar.
No, it's not planar.
Or
Pyramidal?
pyramidal.
Do you guys have this wonderful chart? Let me see if I can find it. Got like a million things open right now.
Pyramidal.
Yeah, it's pyramidal. That's for chart. So I emailed this to all of you. Took the time to form this chart. If you haven't already, I recommend you do note cards where you have the domain and the number that are bonding domains and lone pair domains of that domain. And on the other side, it should say the EPG and the MPG here, okay, and include the bond angles. All right, so right now we were here where we had 6, 5, and 1. So it's octahedral and square pyramidal, okay? So here's the shape. Did everybody get this handout or not?
I found it online, but yeah.
Okay. Shirley, do you have a question? Shirley?
Yes.
Question here shows you're raising your hand.
I was going to answer the question, but then someone else answered the question.
Oh, I'm sorry. Now that you guys are aware, so I'm sorry, Kevin. It's press. I'm fine if I answered your question, not the hand again.
Okay.
Okay.
For Kevin. There we go. All right. So nobody has any questions. Are we okay so far? So the way we draw this now, 3-dimensionally, is we would have fluorines going into and out of the page. Out of the page is marked by a wedge. Into the page is delineated by the dashed line getting smaller. And then we would have a fluorine up here, and a lone pair down there. So what's the bond angle between these?
90.
Good. Note that a circle is 360 degrees, so just divide by however many elements you have. There's 4 elements, so 360 divided by 4 would give you the 90 answer for each degree. And then the bond angle between here and here would be what?
Was it 109.5? Or is that not?
No.
180.
It would be 180 had there been another fluorine down here. This bond angle would have been 180. Okay? But what we're looking at is the bond angle that's just between the fluorines, which should have been a perpendicular bond.
90 all the way across.
But what do lone pairs do?
Just push them
They
in.
make angles smaller.
Smaller. So what happens here is these fluorine, these bond angles here actually get to reduced or smaller than 90. Sorry. I promise you that's a 9. Does that make sense?
Mm-hmm.
Okay. So square pyramidal. Is hybridization going to be on this test?
No.
They sent out interaction, but I don't know for sure. Let me check it real quick.
Okay, well, if it was, what would it be? You could memorize it. Like you could go from the bonding domains.
It's SP3D3.
So you could go,
right?
Well, let's see.
Or no, SP3D2.
SP, this is SP2, this is SP3, this is SP3D, and then this would be SP3. Okay?
Oh.
What's happening is the bond angles that we see in real life don't exhibit, like the p orbitals are 90 degrees to each other. Okay, but no bonds or no compounds are formed 90 to each other. They're always like 109 or 120. They're weird angles. So they figured that they had to be some hybrid orbitals that had partial S character and partial P character. So they were kind of a mixture of the sphere and the dumbbell. But basically what's happening is we're borrowing one of the electrons from the full S to put it in one of the p orbitals to give you something that will bond with other elements. So 2, 3. So for instance, if I had BH3,
So it's SP3 too because of S6.
yes, that is correct, Shirley.
Okay,
Okay, so for this boron in the middle, for instance, what happens is that boron has 3 valence electrons. Okay, so it's got 2 here and then 1 in the P. All right, but to form a sigma bond with each of these hydrogens, it needs 3 single electrons. So what happens is one of these electrons in the S says, "Hey, I'm no longer going to be in the S. I'm not doing good here. I'm going to go over here and hybridize with my P."
Okay.
3 single S2 hybridized orbitals with electrons ready to form on hydrogen. Does that make sense?
Mm-hmm.
Is that too much detail for you guys? Have you not gone into the orbital diagrams yet?
We haven't done it like that. I mean, I knew it previously, but I didn't know the reason behind it. I just memorized it.
Okay, it's fine. If we're at the memorization stage, next test, we're going to be doing what I just showed you. Orbital diagrams. Okay? You guys ready for another Vesper? Did you screenshot this or write it down? What you got to do?
Yeah.
I need help. Dexter.
Matt. I was waiting for you to ask your question. I'm sorry.
Oh, sorry. For the one in how you would draw it and like write down the angles, like why is the other side less than 90? Can you explain that a little bit more?
Sure. It's the electrons. The lone pair electrons right here are repelling the lone pair electrons in the bond. So what's happening is, let me use a bright color. So these two electrons right here are negatively charged. So are the bonds in this electron. So there's going to be a repulsive force that occurs here that pushes on these bonds with the fluorines, and thereby taking this, what should have been a 90-degree angle, making it less than 90.
Okay.
That makes sense?
Yes. So
hey, girls, get up here. All right, give me 1 second. Everybody come upstairs, please. All right, let's do another one.
we need some papers.
What are you guys chewing on over there? Get up here. Upstairs. Come on. All right. What would I do there? I apologize if we did this in web tutoring. Actually, no, that was with Anthony, I believe. I don't think any of us did this one, right? Okay. So let's look at that one. What happens here? Iodine is a
Halogen.
on the periodic table. Iodine is a halogen, right?
Yeah.
So it's got 7 valence electrons times 3 plus or minus. What do we do for this? Add 1 electron since nobody wants to share. 22 electrons total. So we have to draw, there's no choice like that. We do a single bond everywhere. Something we didn't do on the last problem is calculate the formal charges. So let's do that real quick just to be sure. So the formal charge of sulfur, let's do it in our great colors here. How do we calculate formal charge?
It's a too easy thing. Not at all.
So the
Let's try
balance, holy, the microphone is too good, dear. I'm sorry. I'm going to have to mute you. Raise your hand if you have a question. It just picks up every little noise. So here we have a number of bonds is 5 plus 2 lone pair. All right. So it's going to be a -1. And then formal charge of the fluorines is going to be 7 because it's a halogen, minus 1 bond plus 6 lone pair electrons, which is neutral. So the net charge is a -1, so it was okay. I didn't draw my -1 where it should have been on that sulfur. Okay, so back to the problem we were doing. What do you guys recommend we do next? We get a volunteer.
Give the outer atoms their lone pairs.
Okay, so let's dump some lone pairs on them. 2, 4. It's a halogen, right? So it wants usually 6. So there's 12 minus 12. Actually, let's do -4 lone pair or bonding electrons first. So that's 18 lone pair electrons left. And then we just use 12 of them. So what do we do now? We got 6 lone pair electrons. What do we do?
Because it's past the third valence, or yeah, the third valence shell. It can have extra or an extended octet. So you can add 3 lone pairs to the central atom.
Very good. Good job. Okay, so now how many domains do I have?
5.
So right away, you should be able to tell me my electron pair geometry. What is it?
Trigonal bipyramidal.
Very okay. Now, looking at the bonding domains versus the lone pair domains, how many bonding domains do I have?
2.
And then leaving me 3 lone pair domains. So this tells you the molecular pair geometry, the specific name. This is the general shape. This is the specific name of the actual structure that we have here for this molecule. So what is it here?
Linear.
Linear, very good. Okay. What happens is you have these guys are 3 domains on the central one. So that's going to be 360 divided by 3. If these were elements, they would be 120, right? But they're lone pairs. And then the only thing that really has bonds to speak of bond angles is this bond and this bond. And they are on the same plane. And this is 90. This is 90. So the overall bond angle is 180. Okay. Due to the symmetry here, pushing up and down, there won't be any distortion as far as less than or greater than. Any questions here?
Nope.
Okay, let's change it up a little bit. Is grams and atoms and stuff going to be on this exam for you guys?
I know it's chapter 6, 5, 6, and then part of 7. So I don't know exactly what that is, but there might be some stoic on it.
There should be. All right, let's see. Okay, let's start off basic. Let's see. Let's do this question here. How many grams of potassium and 2.14 times 10 to the 24th atoms? How would you go by doing that? What is the link?
Divide by Avogadro's number to start out with.
Okay. What is the purpose of doing that?
So you convert atoms to grams per mole, or to just moles, and then so you're going to have moles potassium.
Good. So we know that in 1 mole of whatever element, it's been standardized to have Avogadro's number, which is 6.02
times 10 to 23.
Atoms of whatever. So now that we're in moles, what can we do?
Convert the amount of moles to, or multiply the moles times the molar mass.
Good.
Or divide the moles by molar mass.
Well, the reason I do this tabular method is so I know whether or not to multiply. I know that if I put moles on the bottom, it will cancel with this moles. Okay? So I know that stoichiometric table that top and bottom must equal. Jasmine, come in. So 1 mole equals this many atoms. So if I'm going 1 mole, I have to write the grams up here in 1 mole of potassium, and that can be obtained from good old periodic table.
22.90, I think.
No, you're thinking of sodium. It's 23.98. But here it's 39.08 grams per mole. So then when you do that, you get 138.95 grams of potassium. Any questions?
Nope.
If I'm using sig figs, how many sig figs would I have?
You would have 3.
3.
139.
Because of this right here. Any questions? Shirley, are you trying to ask me a question? Then mute you. Just raise your hand. Raise your hand. I'll know you have a question.
I don't have a question.
Oh, okay. Somebody's coming in and out, I guess. All right. Let's see. Let's do another one. Let's do.
Hey, Dexter.
Yes.
I'll probably be leaving around 5 class.
Okay, no worries. If you want, I can quiz you later on. Meeting another student.
Yeah, I'll text around not to be later on, probably around like 7.
Okay. A compound in polymer uses 58% carbon. Charlie, can you mute yourself, please? Shirley has the best microphone on the planet. All right, so 58.774% carbon. Actually, let's just start a new layer for this. So carbon is 58.774, and then hydrogen is going to be 13.81%, and then nitrogen is 27%. What is the empirical formula of this compound? You guys did empirical formula?
Uh-huh.
Okay, so what is the trick here?
I don't remember.
You have to convert them to grams.
Let Sandra try. Kevin, let Sandra try. Go ahead.
No,
That's good.
I don't remember.
I'm sorry, I didn't catch that, dear.
I was like, I don't remember. You should continue.
Okay. Shirley, you want to give it a try? Guess not. All right, Kevin, what do we do?
Convert to grams and divide by the.
You're going to assume
divide by the.
It's 100 grams. And then after that, what you can do is just say that these are grams. Now what?
Now you can just divide by the molar mass of each element, and then you'll get a relative amount of moles.
Good. So we convert to moles. So carbon's molar mass is 12.01 grams of carbon and 1 mole of carbon. And here we've got hydrogen is 1.008, I believe, grams of hydrogen and 1 mole of hydrogen. And then 27 grams. Nitrogen is, I believe, 14.1 grams of nitrogen and 1 mole of nitrogen. So when you do these, let's see, you get 4.89, and then 13.9. And 1.958. Okay. So then what you do is you got to divide by your lowest number of moles. N is the symbol for moles. So if I divide everybody by 1.958, Now, each professor and textbook is different. Usually, this answer has to be within plus or minus. Oops, forgot my 5. Plus or minus 0.1 of a whole number. Some professors say plus or minus 0.2 of a whole number. It depends on what they say in your class. But when you divide these guys, you're going to end up with 1 there. Where's my calculator? Uh, 13.9 divided by 1.958 equals 7.099. So 7.010 will work. And then 4.89 divided by 1.958 gives you 2.50. Okay. So looking at that, what do you recommend we do? Are we okay?
Multiply by 2.
Here, I'm going to leave this as 7.099. Why are you choosing to multiply these by 2?
Because 2.50 is not a whole number.
Good. So this is too far away from being a whole number. So we have to multiply by integers until we get close to a whole number. And multiplying it by 2 does give me a 5. And here will give me a 14.018 or 180, something like that. Let's see. 7.099 times 2. 14.198. And then that's going to be times 2, so it'll be a 2. So because this is close enough within the allowed plus or minus 0.2 range, and this is a whole number, and this is a whole number, then we're good to go. So we know it's going to be carbon, subscript 5, and the hydrogen is going to have a subscript of what?
14. Yeah, 14.
And then the oxygen will be what?
It's a nitrogen, but it's 2.
Yes, it is nitrogen. I'm sorry. I was up till 5 a.m. working on the website, then got back up at 8 a.m. and started working again. And
yeah,
I'm a little out of it as I write a 5. 2. That should be a 2. Okay. So this would be your empirical formula. Give me a second. Let me try to calculate something real quick. 5 times. What if I told you that the molecular formula of a compound was 306 grams per mole, and this was its empirical formula? What would the molecular formula be? So,
can you rephrase the question?
Sure. This is the molecular weight of a molecular formula that is obtained by multiplying this by some n. So if I multiply this by some n, I get whatever this compound is. Okay, so I need to figure out what the n is. So the way you do that is you're going to need to find the molar mass of your empirical and then divide that over here to figure out what n is, and then you'll multiply it. So for instance, in this case, 5 times 12.01 is 60, plus 14, 74, plus 28, 74 plus 28 equals 102. So this right here has 102 grams per mole molecular weight for the empirical formula. Okay? So if I take that 102 over here and divide it, I know that this goes in there 3 times. So the molecular formula that I was interested in would be C15H, whatever 3 times that is, 242, and N6. Do you see how I did that? So I found the molecular weight of the empirical formula, then I divided that molecular weight by the molecular weight of the molecular formula. This is the actual molecule, okay, the compound we're dealing with. This is just a base formula that gives rise to this compound. Okay, Kevin, get to class. I'm going to keep working with the ladies.
Okay, see you later.
Just text me, okay?
Okay, bye.
All right, ladies, did you get all that? Do you have any questions on what I did?
No.
Oh, Shirley left too? Did she have class?
Hey.
Okay, it's just me.
Now?
It's just me and you, Sandra. So what would you like to work on?
Oh, yeah, how do you determine if a substance is like polar or non-polar?
Okay, good question. Miss, I skipped tutoring on Tuesday. What happened Tuesday?
Tuesday?
Yeah, I thought we were going to meet for chemistry.
Yeah. I don't know.
I don't either. Okay. Actually, we can look at that one problem we did and determine whether it's polar or not. Let's see if I can find it. There it is. So you see how this compound right here, if I were to look at it, the fluorines would cancel out the dipole moments. Fluorine, which one's more electronegative, sulfur or fluorine?
Fluorine.
So the fluorine would have a bigger electron density, so the dipole moment would look like this. But then there's one that cancels it here. This one, but then there's one that cancels it here. So far we're not polar. Now, if I had a fluorine up here and a fluorine down here, these dipole moments would cancel each other out. Okay? But because this isn't a lone pair, not a fluorine, the electron density for the lone pair is going to be much bigger than over here. So that there's going to be a net dipole going down to the lone pair. So this would be polar. So if you have lone pairs that are asymmetric without other lone pairs, then it's polar. Let's look at the last one we did. Boom, 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 boom. So looking at this one, see we have all these lone pairs, but they're 120 degrees from each other. So when we're looking at it, we're going to have one lone pair that's on the plane, and then the iodine, and then one lone pair going into the plane, and then one lone pair coming out of the plane. But since the angle between them is always 120 degrees, their dipole moments will cancel each other out. The vectors will be symmetric. Okay? And there's an iodine up here, but guess what? There's another iodine down here. See what I'm saying? So all the dipole moments can cancel each other out and give you something that's symmetric. Like, you know, see, if I put a chlorine on each end of these, okay, when I do that, the bond angle is 109.5, right? Chlorine is a lot more electronegative than carbon. So we have all these dipole moments that exist, but since the bond angle is fixed of 109.5, guess what? It's nonpolar. They cancel each other out. Whereas the ammonia is also tetrahedral, But these lone pair don't have another lone pair to balance them out. So the bond angle is not 109.5, it's less than 109.5, and no longer symmetry occurring to cancel out this dipole moment. So it's polar. Do you see? You're starting to see it? So if you have lone pairs that are unbalanced with other lone pairs, then it's polar. If you have elements, even though one's more electronegative than the other, as long as it's balanced out with other ones, like the chlorines, it's nonpolar. Okay? Let's see if I can find one of those on the test for you. This is too easy. You can do this. I believe in you. What is the bond angle in BCl3? Okay, so let's look at BCl3. So this has a valence of what? 3. And this is?
Let's see, so all of them 24.
Who goes in the middle?
7? The one I mean.
So what do we say? What's the EPG and MPG?
Okay, so it has like a domain of 3, so EPG will be equal to MPG, so it will be trigonal planar.
Good. What's the bond angle?
It will be like 120. It will be 120.
I'm teasing you. All right. So then is this polar or non-polar?
This will be polar.
Okay.
Because it cancels out.
This and this are all the same element. The bond angle is the same. So anytime you have bond angle and the same element, it's non-polar.
Okay.
They cancel each other out. Okay?
Okay.
Let's see. Let's find you another question. Okay, here's a good question. So the weight percent M in MCl2 is 36%. The atomic mass of M is what?
Okay, so you like subtract. You take like 100% and take out 36% and only.
What does weight percent mean? Well, percent means fraction over whole times 100. That's what percent generate means. So if we're talking about percent weight, it's going to be the fraction of M over the whole weight times 100 is going to be equal to 36. Are you with me?
Mm-hmm.
So we don't know what M is. We'll just call that X. And we don't know, or we do know chlorine has a mass of 35 point something. Is it 453?
Since you modify it, it's 35.45.
Yeah, look at that. Look at the break. It's pretty sad. You know you don't have a life when you've got the atomic elements molecular mass memorized. Not all of them, but just the ones I use a lot. And there's 2 chlorines, and that will equal, if I divide both sides by 100.36. You see how I did that?
Yes, I did.
Okay. Where X is atomic mass of M. So it's the mass of M over the total mass. This is the mass of M. This is the mass of chlorine. So now if we solve that equation, we can find out what the atomic mass is. So how do we solve it?
Okay, so you multiply 2 by chlorine's mass and then get rid of the fraction by multiplying the whole denominator on both sides.
Okay, good. So if I multiply that times 2, that'll give me roughly 71. And then I can multiply it on both sides, she says. Okay, let's do that. Let's do that. So we're going to have X plus 71 here, and then X plus 71 here. So on this side, it shall cancel, leaving me with X equals 0.36X plus whatever that is. So on AC, so 0.36 times 71. And that's going to give me a 25.56. What do you propose we do now, young lady?
Subtract 0.36x from both sides.
Okay. So I shall subtract this on this side, and if I do it to one side, I must do it to the other side as well. And then I am back here. Oops. So this is going to give me 1 minus that is what? 0.64x equals 25.56. So if I take that and divide by 0.64, I get 39.9375. So how many sig figs do I use?
No, that's 4 6 6, that's 3 6 6, so it has 2, so that is a lot of 6 6, so what should we use?
The only thing that was
the
only given information from the experiment, the one that we can really go by, is that 36%. Okay, so because they said 36%, we can only have 2 in our answer. So if I round that, that would be 40 AMUs. Okay. Do you understand how I did that? Do you have any questions?
No.
Okay. Do you need to write it down? Or screenshot?
I wrote it down.
Okay. I'm going to keep going until you tell me, no more, my brain can't take any more. What are you doing to me, Desta? Given the following reaction. Oh no, you left me? Ooh, what did I do? I'm trying to help you. What are you doing? Come over here. Hello. Welcome back.
Yeah, my line cut up.
Yeah? You shouldn't be mean to the people on the other line then.
Wait, what?
I'm joking. I don't know. I'm tired. My humor's not even making sense. I was trying to say that you were talking to somebody and they hung up on you, but then I was like, wait, maybe she thinks I hung up on her on purpose now, and that's not what happened. So just ignore it. Let's go back to the problem. I have this equation. I tell you that I have 2 moles of this one. And I tell you I have 2 moles of this one. And I want to know what is my limiting reagent and how much of the excess of the moles of the other one do I have left?
That's why we didn't do that yet.
Okay. All right. So if you didn't do that yet, you don't have to answer it. Okay. Let's do this one then. Alrighty then. How many moles of sulfur are there in 1.24 moles of uric acid? How do we do it? What do we do? What?
How many moles of S are there in 1.24 moles of... Okay, so you find the molar mass of H2SO4.
It is given to you, 1.24.
But you find the total molar mass though, don't you?
No need for all that.
No?
You have to use what is called mole ratio.
So you find the grams
Nope.
of... no, okay. Alright.
So we start with 1.24 moles of H2SO4. And we look at the compound and we know that in 1 mole of H2SO4, there is 1 mole of sulfur because the subscript is 1. So that means that there is 1.24 moles of sulfur as well. What if the question said, how many moles of oxygen do I have?
So for this one you have to...
Actually, let's say, how many grams of oxygen do I have?
So you find the grams of... You have like 4 plus the molecules of oxygen, so you multiply 16 by 4.
Yes, the molar ratio. So again, we start out at the beginning. Online, you take this sucker here and you use your mole ratio. Yeehaw. So that mole ratio tells me that for every 1 mole of H2SO4, because of that 4 right there, I got 4 moles of oxygen. And then what I do to myself, I say, hey, I know that I have, for every 1 mole of oxygen, what? What goes on top?
1 mole of oxygen, you have 16 grams of oxygen.
Very good. Very good. Too good. Too good. So now you take 64 times 1.24 to get your answer. 64 times 1.24. Oh, let's start it again. 64 times 1.24 gives me 79.36 grams of oxygen. Does that make sense?
Yeah.
Okay. Do you have it written down?
Do I have?
Do you have this written down?
Yes, sir.
Okay. You make me feel old. Call me sir.
Oh.
So you didn't do limiting reagent, you said?
No, I did not.
Okay, let's do this question. So we got 78 gram sample has N equal to 1.5. What's the element?
So N is the number of moles, right?
Mm-hmm.
So we can divide 78 by 1.5 and then look from the periodic table to check what element has the number of grams.
Smart girl. Good. Let's do it. So 78 divided by 1.5 gives us grams per mole, which gives us 52. This is the atomic number. So if we come over here on the periodic table, 52, we get that's not the right answer, though.
But is it 52 being the AMU or the atomic number itself?
Oh, okay. So it's the atomic mass.
So it will become
51.99. Chromium it is. Good. Good job. All right. Did you guys do molarity?
No.
No molarity? What is going? Okay, what is the percent weight of carbon in C3H8O?
Oh. It's a fraction over the whole times 100.
Okay, so
we find that should I say molar mass of carbon? and divided by the entire mole mass times 100.
Like this?
You multiply by 3 because we have 3 moles of what's the name? Yes. And 12 times 3 plus 1/8. Okay.
Okay.
And we have
So that's going to give you 0.6002.
0.6002. Then you multiply it by 100, which will be 60.02%. Carbon.
Good. Let's do AlCl2 minus Vesper.
AlCl minus. Okay, so you have to like first count the valence electrons.
You have to what?
Count the valence electrons.
Okay. Aluminum has
3. Chlorine has 14. Then you add 1 to it, so everything will be 18. And aluminium will be the central atom. And then we have chlorine to the side. Then you subtract 4 from the total valence electrons, give you 14. Then you add the lone pairs around chlorine first. Then you subtract 12. Then you have 2 lone pairs around aluminium.
Okay. Now what?
The oxide of aluminium is not satisfied, so will you share a chlorine with aluminium or not?
No, because aluminum is in the third column, and it's one of the exceptions like boron that can have less than 8 because it's in the third.
Okay.
Look at its formal charge. Formal charge for aluminum would be 3 valence minus the 2 bonds plus the 2 lone pair electrons is a -1. Okay. Now, if that was another chlorine, it would be a neutral. But since we have an anion, if you remember from our problem, it's holding the charge, that's where we want the charge to be anyway. Okay. The formal charge for the chlorine is going to be 7 minus 1 plus 6, which is neutral. Okay. So what's the MPG or EPG first?
The EPG will be trigonal planar.
Good.
And the MPG will be linear.
So 3 with 1 lone pair is bent. Okay?
Okay.
Or angular. And what is the angle?
It's 120 or less than.
Less, because these lone pairs are going to push down, making this less than 120. Okay? Is this polar or non-polar?
This is non-polar. It's polar.
Which one is it? Polar or non-polar?
It is polar.
100%?
100%.
Good. Because we have that unmatched lone pair, right? On aluminum. If that lone pair was a chlorine, would it be polar or non-polar?
If there was a chlorine there, then it would have been non-polar because it will be a three-dimensional thing, so it goes side by side.
The bond angle would be the same, and the elements would be the same. So the dipole moments would cancel. Okay?
Mm-hmm.
A sample of chromium-3 oxide. Are you in my office?
Mm-hmm.
Contains 0.370 moles. How many moles, how many grams of oxygen are there?
How many grams of oxygen are there? Is it oxygen gas or just oxygen?
How many grams of oxygen?
Okay. So you do the mole ratio, but then you have to find the molar mass of chromium-3 oxide first, and that would be chromium has a.
Why would you need the molar mass of chromium-3 oxide?
Because you're gonna use a mole ratio. This is mole ratio. The mole ratio, so you have 1 mole of Cr2O3 will give us a specific number of grams.
Yeah, but why do we need those grams when we already have the moles? The reason you want the grams is usually to go to the moles, but you're already given the moles. If I told you there was 125 grams of chromium-3 oxide, find the molar mass, divide by it to get the number of moles. But here, I gave you the number of moles. You understand what I'm saying?
So,
like if I gave you a grams, number of grams, then divide by molar mass, which is grams per mole, to give us the moles. Then you can use mole to mole ratios. Okay, but here I gave you the moles to start out with, so you don't even need the molar mass of the chromium-3 oxide. Do you understand?
Okay, so like, how do you solve for this one then?
Just use the mole ratio. You know that you've got Cr2O3 is what you told me, right? So I know that in
1, 2, 3. Cr2O3.
Isn't that what you told me? 1 mole,
yeah,
that has how many moles of oxygen?
3.
3 moles of oxygen, and we're done. Oh, no, I asked you for grams, so then we got to convert it to grams. So then we know 1 mole of oxygen gives you 16.00 grams of oxygen. And then multiply that out and you get your answer. So that would be 48 times 0.37. .76 grams of oxygen. Okay? Do you have this written down? Okay. Let's look at this problem. Let's look at So I made the number of sigma bonds and the number of pi.
We didn't do this one too.
You didn't do this?
No, but I can guess that the number of sigma bonds will be 1, 2, 3, 4, 5, and pi bonds will be 2. No, 3.
3 pi bonds, yeah.
3 pi bonds.
There's 2 here.
But we didn't learn this then. We've not learned this yet.
Okay, that's one. Let's do one more, and then I need to let my dogs out for a little bit. You can join the late night session if you want. 36 grams of N2 or 18 grams of A3, O3. Which one has the most atoms?
Okay. Do you like just multiply by Avogadro's number to see or not?
No. You got to first convert to what before you can use Avogadro?
To the number of atoms?
Number of moles.
Moles?
Mm-hmm. Avogadro is the link from, you got to get to moles before you can get to atoms. So what you do is you, for instance, we know that nitrogen has a molar mass of 14, but since it's N2, it would be 28.02 grams of N2 and 1 mole of N2. And then we can then say 1 mole of N2 has 6.02 times 10 to the 23rd atoms. And then if we did the same thing for the 18 grams, we know that there's 48 grams in 1 mole. And then we know 1 mole has 0.02 10 to the 23rd. And you wouldn't even really need to calculate this. You could just look at the ratio. This is going to be 1 over 28, and this is 1 over 48. But this is twice. So this is twice that, right? So that would be 2 over 28. So that's 1 over 14 versus, I'll just calculate it out. Who cares? Here you're going to get 1.5 e to the 24 atoms. And then here you're going to get 6.8 times 10 to the 23rd atoms. So as a result, this has more atoms. Okay, so always convert to moles first before atoms. Alrighty?
Okay. Yes, sir.
Okay. Well, work on that review sheet some. I'm going to try to make it up there tomorrow and answer some questions for you guys, even though I probably shouldn't, as far as I don't like, advocating last-minute studying. But either that or I might just answer questions online for students or do another online review session. Okay? But do as many problems as you can tonight. I think you're a little shaky on your empirical formula. Practice some of your polar, and you're shaky on some of your stoichiometry. So make sure you practice this stuff as well.
Okay.
Okie dokie. You should do fine, though, overall, if you do practice a little bit tonight.
Okay.
And I'll send you guys the review. I've been recording this review. I'll send it to you later tonight.
Sure.
I hope I helped. Was this helpful?
Yes, sir, it was.
Okay. Are we meeting tomorrow at 2 o'clock or whenever you're scheduled?
I have a class at 2.
What time did you sign up for?
4.
4 o'clock?
Mm-hmm.
Okay. All right, dear. Well, have a good evening.
You too.
Text me if you get stuck later.
Sure.
Bye-bye.